So today's topic is about III filters. So this is the last session. Yoo-hoo. So we don't have the session next week anymore. And let's see about the IIR filters. I will show you some couple of things on the on whiteboard what we are talking about today. So basically, first IIR filter, the easiest one to design, or actually the only IIR filter you can design in pen and paper is practically the notch type of band stop filter, where you have basically you set a pair of zeros on the unit circle, meaning that in this angle omega n, the omega n, we have actually total attenuation of the signal. Okay, so on that angle, so we have the total attenuation. Nothing comes out on that frequency. Then basically, if we had only this one and all the poles on the origin, which would be FIR filter, our amplitude response would be actually like this. Okay, however, if we put a pole pair on the same angle as our notch, we will actually get amplification on this region, and even better, think of a signal or frequencies around here. We have equal distance to all the zeros and poles, meaning when we are looking at the amplitude response, we will get simply 0, okay, product e to j omega minus ck and divided by e to j omega minus pk. Okay, so both of these are same. So for example, on this point, this distance and that distance is about the same, meaning the ratio is 1, same for that. So around 1, not exactly, but so basically what we are getting is something like this. Whoops, it's actually better than that. So we have nice unity gain on the pass band, and then we have the notch band right, the stop band right there, where we want at the center frequencies omega n. Okay, this also have a control of the minus 3 dB point, since if you take a magnification of that one and go to basically, if this distance is a and you take the same distance here, this one actually becomes roughly square root of 2 times a, meaning that in this equation you will have a divided by square root 2 times a at this frequency. So basically, if you want to have certain minus 3 dB half width, so this is 2 times a, then you just plug it in this equation on the as the distance from pole to the unit circle, which is at the same time basically 1 minus radius. Okay, so that's the first part, I think. Let's take a quick look at how does this one look like in MATLAB. right there. There we go. So this is the band stop notch filter by setting the simply this center angle setting A of zeros and poles. Okay, so first we need a couple of frequencies like maybe a stop sampling frequency. So let's make it 2000 hertz. So this would be something for example a data acquisition system. So data acquisition system sampling rate. Then we will have this stop frequency, Fs, with the lowercase f. So, or actually, let me mark it Fn, then it will be exactly the same as there. And for that one, see what would be good. Let's mark this one, for example, 250 hertz just for fun. So then we have the this notch frequency. The next what we need to do is actually just change this one to the angular frequency, omega n, which can be done simply by dividing this one by Fs times 2 times pi. Okay, where this one actually comes from. Okay, yeah. Nyquist frequency is actually on the angle pi, and then 2 pi is back to the sampling rate. Okay. So this is the corresponding angular frequency. Okay, so next point, we set the zeros. So ZZ equals 2 exponential of J semicolon minus J. So this is the complex conjugate pair times pi times omega n. Yeah. So this point here is simply e to j omega n. Did I have the pi already there? Yeah, oh, sorry. Yes, yes, I do. Now I have the pi twice. Okay, there. Simply j times omega n e to minus j times omega n. All right, so puolipiste, semicolon. So this is a semicolon because of it's basically you know, column vector. There. And seeing is believing. I'll just show the z plane of ZZ, and let me put the poles, both poles at the origin. Oops. There, just for fun. There we go. So this is still the FIR system because the poles are here. Now we just change these poles close to the unit circle. On that, the angular frequency, which is basically corresponding to our half width of the filter. Okay, so so the poles. We need to set up the half width HW. For example, does it show up? Maybe. Okay, I'll mark it 50 hertz. So 50 hertz half width, half width, because that's plus and minus. Okay, so corresponding the angular rate would be simply that HW divided by Fs times 2 times pi. Okay, yeah. So that's the angle. But at the same time, since we are on the unit circle, it's also this distance. There. And this is directly this A. So our range of the pole would be 1 minus omega HW. Okay. Okay, so, and then we can actually generate the poles, which is simply this R times ZZ. So the difference between the poles and zero is that on pole you just have the R times this distance times the same exponential on that angle. Magic of the complex numbers. All right, so the poles at the same angle as Z, but range equals 1 minus A. There. And this would look like where did it go? There. Okay. Looks somewhat similar to my drawing there. Sometimes I get lucky. Okay. So then we just need to figure out what are the corresponding system coefficients. So system coefficients or system parameters are BB is the polynomial which is defined by the zeros, and AA is the polynomial coefficients defined by poles. Okay, yeah. Let me just plot also the BBs so you can see. Okay, so it looks like that. So we have a nice the upstairs is just 1 minus square root of 2, 1. Oh, that's nice. How did this one come here? Nice even number. Okay, and then we have a couple of values there. And now we can do all kind of magic like impulse response. Compared with the exercise 3, you can calculate the impulse response for the system. So, for example, like this. And is equal to filter BBAA double NN equals 0. I think this will do the impulse response. system. NNIRSP. Oop, of course. There we go. So impulse response look like it's infinite impulse response system, of course. Yeah, that was what was expecting, since the poles are not anymore at the origin, and there are no canceling poles either. Okay, so yeah, that's the impulse response, and then let's see the frequency response. B, B, A, that many points, and sampling rate. And what I'm expecting to have is 250 hertz notch frequency with a full width of 100 hertz. Let's see what this look like. Wow, not bad. It could be worse. 250 hertz exactly here, and then the 3 dB points plus minus just around the plus minus 50 hertz from this one. Yoo-hoo! Yeah, I know. So that's a filter you can actually design just by pen and paper. But the rest of those filters, rest of the IIR filters is not that easy. Let me quickly go through the bandstop notch. Do we have? Okay, median. Wow. Okay. Well, there are some methods actually mentioned in this slideshow, what you already have watched, right? So they are the direct design method is exactly like this, and only that's somewhat the only kind of filter you can actually design this by this way. One, and where to use it? Okay, if you have a small system, small microcontroller system which doesn't have too much of computing power, you can still filter out 100 hertz or say third harmonic, which are the most common noise signals on a small microcontroller systems which are sampling something. One warning though, let's take also a look at the look at this one. So if your sampling rate is not exactly correct, but for example, you have even 1% difference. 1% difference in this scale would mean actually a 10 hertz change in the real frequency, meaning that you are really rapidly losing the whole idea of having this one as the filter if you don't match exactly the this frequency. Either if the this input frequency is not exactly, well, it is. The whole Finnish or if any say European country network gives you really sharp 50 hertz basic fundamental. It's much better than what you can do just like that. But where you have the jitter is usually on your sampling clock, on your microcontroller, unless you use a say a real crystal oscillator outside. Then you need to, of course, have some sort of calibration on it, or measure where your highest noise peak is and adaptively follow that frequency and tune your filter exactly on that one. So that will be, say, next course about adaptive filtering. but the principle is quite simple. You need a control loop where you measure this frequency and then design the filter and basically just tune your notch filter to that frequency. That'll work. Okay, so where's the that'll work. Okay, so the next point, how to design the other filters. I will show you the fast way. Say bilinear transformation. It's one way. You have heard about the classical filters in analog circuits like Chebyshev, Butterworth, Bessel, elliptic, that kind of filters. Those are analog filters. But on the analog filter, you can actually change it to digital filter simply by setting the S equals 2 over T. Okay, I need to take a look at Z minus 1 divided by Z plus 1. This is called the bilinear transformation. So if you have, for example, that, let's see, voltage control voltage oscillator. The other word is the Sallen-Key low-pass filter with the h of s something like 1 divided by s squared plus a times s plus b, something like that. There you just, with the sampling rate known, you just plug this one here, you'll get the h of z. Okay, this here maps your system on frequency scale so that basically on S-plane you have the j omega on the imaginary axis. This bilinear transformation takes actually and warps the imaginary axis of S-plane a little bit with some, say, violence. It takes the minus and plus infinity and twist it like that. It becomes unit circle here. So plus minus infinity are actually here. Meaning that for low-pass filter, if you have the original low-pass filter, something like this, that goes forward and forward, on Z-plane actually this becomes, with the Nyquist frequency, the frequency response goes to 0, but it starts warping this amplitude response, and it's not linear anymore. So, well, not linear, but this is not anymore as nice logarithmic, so that you will get this. You can directly see how many decibels you get for decade. It comes a little bit more complicated. But anyways, with this method, you can still maintain a solid cutoff frequency for the system. And yes, you can still do the design of the filter based on the filter parameters. But just wondering where is the... no, someone has stolen the wipe. Okay, I don't need that one. Okay, so let's take a quick look at that one. That was the notch. and then we have the classical filter. Okay, Butterworth, Chebyshev one, or elliptic kind of filters. Basically, this design flow goes like that. First we design the analog counterpart, and then use the this bilinear transformation. Well, you don't need to do that since basically we have MATLAB. So MATLAB does it for you, but that is behind of that kind of the design method. So next, let's see. Let's take a look at how these kind of systems can be designed. But before that one, I want to take a look at exercise template. Okay, we have rand stop notch filter, zeros poles, plot first 25 values of impulse response. Excellent. So we have design IIR low pass filter with the following properties and verify the design from amplitude response graph. Compare the previous filter with the exercise 4.3. So compare with the similar design you made for FIR systems. Then design again an IIR and match the requirements you determined in for exercise 4.7, comparing it again, and then we have a couple of things. Okay, I will show you first hints for the part 9 and 10. So I just need to take a picture of that one, and then and the paper companies are happy. So we are basically going through that stuff. So let's think first something analog. Okay. You are young people, or well, youngish at least. So what is the lowest frequency you can hear? 20, yes, and highest? Okay, good. Does it say it there? No. Okay. And our natural way of listening or hearing is basically, it's a logarithmic scale. For example, if you play any instruments, then 1 octave is the doubling the frequency. If bass note 440, then the next harmonic would be 880. The next is double of that, and so on. So natural way of hearing these frequencies logarithmic. And that's why you actually mark it like this on the border diagrams. So that's the natural way. And also dB is the natural way. When you double the power, then basically just one step in the in your hearing. You basically, and then you double that one, you hear just about, okay, now it gets the 0.3 and or something like that. So for example, the volume of between 1 and 11, there's something like, depending on the amplifier, about 100 dB amplification there. Okay. And hearing, basically, based on this one, your base hearing, or hear low frequencies on this range, about 2 to 200. So this is the base. Then on high frequencies, you actually hear something like that. So that's the high frequencies. And then the middle range is somewhere in here. So basically, in your car stereo or something like that, you have two adjustments. One is for this one, only up. Low frequencies only up, right? It cannot be turned down. High frequencies up or down. And then how about this one, the middle range? Why it doesn't have the control for that one? Yeah, it's just the volume, exactly. So this is basically the everything. These are compared to the middle range, and this is just the general volume. Good. So this is it. This is what it looks like in analog world. In digital world, it looks different. First of all, we have the Nyquist frequency, and then if this is the say 22.05 kilohertz for 44,100, then this 20,000 is here, and 2,000 is, well, somewhere here, and that's about the 200. All right. So when you're designing a filter bank for digital filter, you basically need to still think analog, especially on, well, these overlapping zones. You need to have just about the same, just about the same transition bandwidth on both of the base and middle band, so you don't get any extra warping of the amplitude response on that range. The same here. So in the digital domain, it would look like something like this. And well, you don't need to cut that one. You can go it up to the Nyquist range. Okay, good. So 3 filters. And how to make these filters? There are different possibilities. But this is my recommendation. Do those filters so that actually you are not even trying to combine the filters, but make the high pass filter, the mid-range filter, and then the low pass filter separately. Then you would have the gain blocks here, H. Well, there's on the exercise, there's also the gain for that one. In reality, that will be a common gain for everything. Like that, and then summing junction here at the end. Just 3 different filters. Okay. Then another warning. You might actually get this mid part filter so that it has, say, tens of orders of magnitude, tens of orders here. And implementation of that one as a direct form filter would give you some trouble. So in case of that one, you might actually considering to make it as a cascaded high pass and low pass filter, and just use a filter, the output of this filter to the input for that one. Otherwise, you might get a little bit funny results if this one goes haywire on the order number. Okay, but how to make this one happen? Beats me. Ha ha ha. All right. So how to make it happen? I will show you my favorite tool in MATLAB. It's called FDA tool. That's the best filter design and analysis tool, where you can basically select different methods. For example, here is low pass, FIR equal ripple is one of the designs. Well, so let me just click something here to see. Okay, there. Design filter. There. Click. Haha. Equiripple. This is one of those optimized methods. It optimizes this ripple on passband so that it does not exceed some number, but it just goes and goes by it. And then also the this stop band attenuation is also nice and flat. Okay, and you just plug in numbers and it gives you the design. The design methods for IIR are basically right there. So we have the Butterworth. You're familiar with that, right? That's the flat passband response for Butterworth. Chebyshev type 1, meaning that it has the ripple on the stop band, and then basically this one goes as goes to the infinity. Chebyshev 2, was it the other way around? Elliptic, you get something else, maximally flat. Okay, these three of here actually are those more sophisticated, the more sophisticated optimizing methods. But these four first ones are the classical filters, still classical filters, but using the bilinear transformation, that filter is transformed into the digital domain. Good. So let's take a quick look on those designs, so how it works. You just click Butterworth. Well, let's see what this one looks like. Ta-da! Okay. Perfect. So 10 kilohertz cutoff frequency and goes down. This is the warping I was talking about. So in reality, this is, let's see, minimum order. Does it say the order number? Order is 31. Okay, that's kind of stretching already. If you use it actually a direct form, but okay, the structure. Direct form 2, second order sections. That would be a little bit more advanced stuff on the second course of digital signal processing. Basically, how to improve the performance of the system. It's quite easy to actually understand if we take a look at the filter coefficients. So this is now actually a cascaded second order section, and each of those sections have a different numerator and denominator polynomials, meaning the system coefficients. So it fundamentally looks like that, but a long chain of it. And as we can see there, the numbers are here, say all within plus and minus 1. Let's make something bold and change the structure back to direct form 1 and just simple first or the 31st order section, convert to single section, and what happened to our polynomial coefficients? On numerator, we have 1, 2, 3, 4, 5, 11 zeros here on the smallest number, and the biggest number is somewhere here, only 1 0 after decimal. So it's a 10 order of magnitude difference in between the smallest and the highest value. Same thing for denominator. So we have the denominator polynomial. Okay, here we have well, even more, 12 numbers, and 12, and here we have okay, so something like 14 orders of magnitude difference in the smallest and biggest number. Now think of the convolution, what it does actually for calculations. How much the smallest number matter here? Nada. But it still affects on this system. Still, those when you are calculating it, it just increases the amount of the calculation errors. So for that reason, we basically usually use the second order systems on higher order of magnitude systems. All right, let's go back. Let me click that one and design something else, and then design that one back. I think then it goes back to the second order section. Yeah, good. But anyways, this system also can show you the impulse response, how it looks like, step response, zero pole plot. Nice, right? Oh yeah. Group delay, phase delay. Yeah. What else? The magnitude response, the both magnitude and phase response on the same graph. And yeah. One more thing, since you are actually working with microcontrollers and SATs, how about making a analysis on? So this is again a little bit advanced stuff, but you deserve it. Quantization of data. So if we have double precision floating point, that is your system response. But if we have fixed point system, fixed point, meaning microcontroller with 16 bits, or let's make it even smaller, say 8 bits of calculation accuracy. All right, where does it go? Amplitude response, are they still the same? No, okay, yeah. So that's a big difference already. So 8 bits cannot do much of this system. I think 16 bits would be already a good number. No, it's still going haywire. 32 bit. Okay, it went broken somewhere. Sorry about that. So basically, but anyways, you should be able to actually check what is the difference between. Okay, so yeah, so this is a good example actually. If compared to single precision floating point, doing it double gives you about 300 dB here, but when you go to the single precision floating point, this filter basically cannot do more than 150 dB attenuation. Although 150 dB attenuation is a lot. It's already a lot of attenuation. Okay, but that was something a little bit extra curriculum. The most important point basically is just to be able to do the design and analyze the, for example, the impulse responses, zeros, poles. Maybe look at the this one, and actually, if you would be implementing this one on a microcontroller environment, then you would just click here, generate C header, generate there. Okay, FDA coefs.h file came out, and okay, of course it's on there. So this is just simple coefficient file using double precision floating point numbers. So it's a an array of arrays. So each section actually has the well, for numerators it has this how many sections and by 3. So it's the numerator coefficients there, and then we have the same for denominator coefficients somewhere here. Okay, same kind of table. Yeah, so you can actually implement those filters, what you design here, on the next course or in real life. Anyways, so then if you want to get the filter coefficients or some other files, other information to MATLAB. Now let's go first to the design. Okay. There we. No. There we go. That's the design view. Okay. Actually, if you have a value here defined, okay, FS I think already have. So you can use on this tool those workspace variables directly. So that will be FS, for example, and then say 100 hertz stop and starting at 200 hertz design filter. Yeah, so you can actually use these directly, the workspace values in this tool, or you can also, all right, export any values to workspace. So this is MATLAB workspace, export as objects, for example, discrete filter HD, and export. Now we have the filter design as filter object on our system, so we can start using that one instead of B and A. So now just remember that this HD actually combines both of them. So if you're doing the frequency response, for example, then you would just say HD and how many points and sampling rate. Hopefully this will come okay. Yes, it did. So you can directly use those MATLAB workspace variables in FDA tool, and you can then export to the this workspace any of the results what you have done in the FDA tool. That's nice. Good. So, any questions? Okay. So this is the probably the most fun exercise on this course. So yes. Hmm? Oh, okay. Yeah. Let's see. By magic. Just a moment. I will show you the magic. Order number is actually shown here. Yeah. Order number. Earlier on that design, I have 32 here. Or was it 31? So yes, order number 14, which means 7 second order sections. This shows what kind of structure this filter has. All right, what else? Yeah. And under here you can do all sorts of stuff. So this is the ultimate tool for making any filter, and this actually works. Nice. Good. So, any other questions? If not, then let's take a quick look on. Yeah. So that's more or less clear. Yeah. When you are doing, or if you are doing those exercises, FDA tool now, basically that they write the comments. Well, of course you don't have the comments there. So do some other proof there that you have done the deed. So, for example, a screen dump of the design window, that'll do just fine when you have the parameters like that there. So, and maybe with the amplitude response, then basically it's even more clear. Good. Otherwise, let's take a quick look here. All right, so deadline for this, which is the last exercise of the DSP part, is next Monday. So next Monday we do not have a session. Yoo-hoo. If you have any questions, well, ask them those today or send me email. But my show is done.